speaker is Pierre-Luc from McGill University, and he is going to talk about multi-step methods using matrix statistics.
Okay, thank you. So just to say before starting, this talk is more about numerical efficiency rather than data efficiency. Although I'm looking forward to move to data efficiency, but I had to go through that numerical stuff in order to understand my problem first. So just to tell you a little bit about where I'm coming from, I'm working on the problem of temporal abstraction and reinforcement learning, and in particular I want to understand how to learn temporally extended actions from a representation learning point of view. And I think really the notion of representation learning has been key to many successes in RL. Some of these examples you might be familiar with, especially from the point of view of learning state representations. So that has led to, for example, to the famous TD Gammon, Watson recently, the video games with DeepMind and the Atari games, and AlphaGo just last year. However, in all of these systems, really, they're all lacking this notion of temporal representation, or the ability to plan over temporally extended actions over different time scales. So that's what I'm trying to do. And over the last 2 years, I came up with this system called the option critic architecture, and that we've been able to apply to the Atari games. So what you're seeing just here is the game of Sequest, and we've been able to learn in a fully end-to-end fashion temporal abstractions and state features. So what you see up there are like transitions from options to options that were discovered fully autonomously. So if you're interested, you can read our paper. It's a AAAI 2017 paper. However, what I quickly realized is that if you are to learn temporally extended actions only from the discounted expected return, what happens is that the time scales of your option quickly decreases over time. And it's something that is expected in a way, because from the point of view of optimizing the expected discounted return, the best thing you could do is to collapse to single step actions, because anyway we know that there exists a greedy policy that achieves the optimal. So there is some kind of mismatch between what we're trying to achieve and the objective that we currently have. So this has led me to go onto a journey to understand properly how we should phrase that problem of learning temporally extended actions in reinforcement learning. And in order to do so, I had to come up with the proper tools. So last summer, I started thinking about that problem and writing down what it truly means to learn with options. But really, I had to come up with new tools in order to do so. And it all started by finding more or less randomly this book that I found for $2 on Amazon in the used book sections, and actually turns out to be extremely valuable. It's called Contracting Markov Decision Processes, a book from the 70s by these Dutch guys. And what happened is that I opened up that book, and then I quickly saw that equations over here, and then my brain pattern matched what I knew about options with the structure of that equation over here. So what you see here is a generalization of the Bellman operator. So the generalization is that instead of looking only one step ahead in order to back up values, you have this expectation over t steps, where t is a random variable. So what Van Noonen did in the 70s was to study this kind of generalized Bellman operator, although he didn't call it this way. So that's how I call it, but you won't find that in the book. So this is a generalization of the Bellman operator, and then Van Noonen presented different results regarding that generalized Bellman operator. So here t as really the notion, as the meaning of a stopping time. So what I'm going to do next in the next couple slides is to open up that expectation and write it slightly differently. So in order to do so, it's useful to think about not only transitions and trajectories over state action pairs, but also over that augmented state space where you have state action and termination events. So that doesn't mean that your algorithm is going to have to sample termination events, but for the sake of writing down the map, that's how we think about it. So I will write a lambda for what I called a termination function, but really has more the meaning of a continuation function, but it's just to keep the terminology simple. So with probability lambda, your process continues, and with 1 minus lambda, the termination, your process terminates. So by termination, I mean not termination in the actual environment, but termination of your computation. So when you're backing up values, you terminate your backing up process. Okay, so an MDP, a policy, and a termination function induces trajectories over that space, and I use the notation sharp to denote the event of continuing, and bottom to denote the event of terminating. So we can describe the dynamics of that process with these operators. So these are just operators over that augmented state space. So P sharp here is the transition operator to the next state, and with the continuation event here. And similarly, we have termination operator here, P bottom, where with 1 minus lambda, and 1 minus lambda means termination. Okay, so with these operators now we can start doing cool stuff. So we can define something which I called Lambda Models, but in fact many people have come up with similar ideas under different names, so it's just to keep the terminology consistent. But Lambda Models are in fact what Sutton used to call beta models in 95. Okay, so what we can do with these operators is we can now learn two kinds of models. One model is what I call a transition model. So it answers the question of what is the subprobability of starting in S and terminating in S prime. And similarly, we can have a model for the expected discounted return if you are to start in S and run your process until termination. Okay, so using these operators, we can write in closed form what would be the solution to these two kind of models. So this is just one explicit way to write these expressions. You could also write Bellman-like equations to express the same ideas. So if you open up Sutton's beta models from 95, you will in fact find very, very similar equations, except that perhaps here the presentation is slightly more general because our termination function is over pairs of states. Okay, so now what we just did is that we started from this generalized Bellman operator from Van Noonen, and then I told you how we can think about it in terms of an augmented state space, and then how we can think of building models to describe this expectation operator. So we can go from this representation to this nice linear form here with the reward model and the transition model. And here I'm just plugging back the equations I've shown you. And using Newman series expansion, you can obtain this form here where you have an inverse. Okay, now that's the cool part, and really the gist of this talk is that this form over here is special. It's a matrix splitting. And this is something else which I found by randomly buying books on Amazon for $2, and that book from Richard Varga in 62. So the concept of matrix splitting was introduced in actually I think in the 50s as a way to speed up iterative methods for solving large linear systems of equations, at least large for the 50s. And the idea is pretty simple. Say you have a linear system of equation, AX is equal to B, then the idea is that you will split the matrix A in two parts, M minus N. And then using M and N, you can define some new iterations of this form. So these two forms are equivalent. Okay, so now you will run these iterations where you take the inverse of M times B, and then the inverse of M, N, and your current solution. And this thing can be shown to converge if the product of M inverse and N, the spectral radius of these two matrices, is smaller than 1. So you might think that this is some kind of exotic idea that finds a little connection to reality, but in fact, here's a trivial matrix splitting, which is hidden in our value iteration algorithm. So when we do RL or when we do dynamic programming, our A matrix is really identity minus gamma p pi. So here's a trivial splitting. You say, well, M is going to be identity, and then N is going to be gamma p pi. And then if you follow the blueprints from the previous slide here, well, the iterations that you get are simply this. And this is just describing what we do when we run value iteration for policy evaluation. Okay, so it's not such a far-fetched idea. Now, something interesting is that historically, this idea of matrix splitting was highly influential in the development of preconditioning methods. So the idea of preconditioning is that, imagine you have our AX is equal to B. So what you do is that before solving that system, you take some preconditioner matrix, you multiply it with A, you multiply B with that preconditioner, and then the hope is that solving that transformed system will be simpler. So you see here, I just rewrote the iterative representation for the matrix splitting in a different way. So here M inverse interacts with A, and if M is equal to A, well, these two terms here will just cancel out. This will be identity, and on this side, we'll have the solution to our system. Okay, so that's just an example of an optimal preconditioner, but it's perhaps a rather dumb preconditioner, because solving for that transform system is just as hard as solving the original problem. And now that brings me to the notion, I think it connects really nicely to the notion of representation learning. For me, what is a representation? It's a transformation of a problem such that thinking and reasoning in that transformed problem is easier than thinking in the original problem. So when I was preparing my slides, I was thinking, when I was a teenager, I thought it was cool to own a binary watch. So I bought one of those watches, and then it was really cool. But the problem is it would take me 5 minutes whenever I wanted to know what time it was, because it's perhaps not a very efficient representation of the concept of time. So then perhaps better representations would be with these kinds of watch, where here it's like really clear, you can read really quickly the time. So it's just to say that this captures, I think, the idea of a representation, and it connects nicely with notions of preconditioning and matrix splitting. Okay, so now let's just go back to our matrix splitting equation and our generalized Bellman operator. So our generalized Bellman operator led us to a form that can be expressed in terms of these models, and these models really are a matrix splitting. So the generalized Bellman operator induces a matrix splitting or a transformation of an MDP. Okay, so similar ideas were actually studied in the 70s as well. This was called the pre-inverse transform. Now, what's really cool is that this generalized Bellman operator, in fact, captures a lot of the multi-step method in RL. It's not just a theoretical tool. It explains a lot of methods. So in particular, if you think of the choice of lambda is equal to 0, well, that leads you to value iteration, or for policy evaluation. If you choose that funky indicator function for the termination function, well, you recover Gauss-Seidel value iteration. If you get this termination here, you get Jacobi, and now maybe closer to RL, is then you can also recover TD lambda, successor state representation, the beta model from Sutton, and back to my original problem, you can talk about options under the same framework. So options being temporal abstraction. Okay, so just to be clear, for example, in TD lambda, the corresponding splitting, if you look and do the same exercise, the corresponding splitting is M is equal to identity minus gamma lambda p pi. So lambda here really refers to the lambda parameter of TD lambda, which in its original form was a constant, and then N is of this form. So you plug this in our Bellman equations and you get these equations. I'll show you a bit later what it looks like when you have features, and if you're familiar with these kinds of algorithm, you will recognize the form. So what I want to say is that now this new point of view gives us a new interpretation for the lambda return. So I think it's actually in Watkins' PhD thesis that the idea of the lambda return presented in terms of the forward view was first described. So that's one way to talk about TD lambda in terms of the forward view and its backward view. So this is the view that you might have first saw when you learn about TD methods. So the backwards view referred to the implementation of the forward view, and we implement the backwards view using this LHB trace vector. So the update equations for the LHB trace vector looks like that, and the corresponding forward view is like this. So this is saying that the forward view is a convex combination of n-step returns. So this G here is a random variable, and it's the return. Okay? So what's cool is now you look back at these matrix splitting equations, and what you find is that in fact this can be written in matrix form like that, and our backwards view LHB trace vector just becomes an equation of this form. Where did I get this equation? Well, if you ask yourself, how can I invert M inverse like this? How can I take this inverse? Well, you can expand it in terms of this summation like this, and then just write it recursively. So this recursion here describes how you can obtain M inverse. And if you pattern match this with the update equations for the backward view, you see that it's very similar. So at this point, it's rather preliminary, but I would want to say that I think that another way to think about LHB traces is just as a way to compute a polynomial approximation to M inverse. Okay, so now a bit closer perhaps to the data aspect. You can also think of the projected generalized Bellman equations. So what are projected Bellman equations? Well, these equations here describe the solution, the fixed point of algorithms such as linear TD, or if you have linear models and you plan over that model, well, the fixed point is described by these equations. Here what I'm doing is I'm taking the generalized point of view, and I'm looking at the projection. So this big pi matrix here is the hat matrix. Phi is a matrix of feature, and theta is a parameter vector. So if you play around with these equations, you rearrange the terms, you can get this expression, and this term in particular is what Sutton calls the key matrix. So I think it's the term he uses in his 88 paper on the analysis of TD. So the key matrix is key because that's how you will find out if your algorithm will converge. Okay. So what I want to show you is that we can also obtain generalized projected Bellman equations that look very similar to the regular TD0 case, except that now we have this M inverse in there plugged before the A matrix. Okay, and then when you look at the specific case for the splitting of TD lambda, and you plug the M inverse of TD lambda, you get these equations. Now you Google Boyan's LSTD paper in 96, open up the paper, look at the appendix, and then you're going to see exactly this form. So just to say, we took a different detour and obtained same equations from a different perspective. So really, this notion of a generalized Bellman operator, the way that Van Noonen described it in the 70s, and in fact underlies probably all of our multi-step RL methods. What I showed you today in particular is that we can write down this expectation operator in a different form such that we induce a matrix splitting, and that matrix splitting has a very nice interpretation from the point of view of representation learning and preconditioning, and it opens the way to the design of many new algorithms. And to go back to options perhaps, unfortunately what this theory doesn't tell us is really the data aspect, because it's only looking at the asymptotics from a purely numerical perspective. The best thing you can do is to set lambda to 1, and then you will get the fastest convergence. Because if you remember, spectral radius is M inverse times M. If you did the math, you'll see that setting lambda to 1 is the best thing to do, and it's not surprising. That's what we've been knowing for a long time. If you read Van Roy and Tsitsiklis 97, you'll see that's the same thing that we obtained. But we know that in TD lambda, we have this bias variance trade-off. Sure, lambda 1 gives you faster convergence, but it also brings more variance. So we need to take into account that in RL, we're learning from data, we have noisy samples, that doing function approximation is imperfect, and that our agent, in a sense, are bounded, or they're computationally bounded, or they're bounded by the other factors that could be also physical. So I don't have a new way to explain you today the bias variance trade-off in that setting, although that's where I'm going. And in particular, I'm also wondering what's the right trade-off for this lambda parameter. Because as you've seen, perhaps I went too quickly, but in this table, this representation in terms of matrix splitting also encompasses options. So answering the question of how to set the lambda parameter in general would be useful for both TD lambda and options as well. And I'm particularly interested to design algorithms that learn that trade-off automatically without a human intervention. So I'm done here, and I'll take your questions.
Questions? Have you started looking at some, let's say, relatively simple MDPs and actually play around with that setting of lambda and see how it behaves when you actually go away from the pure theory, but actually try to start applying this? Do you have any beneficial effect? Do you see anything coming out of this?
Yeah, so at this point, I'm still wondering whether I should look at this from the policy evaluation case or more the control case. So there's one slide that I deleted, but I'll just say it like this. You can also generalize control algorithms in that setting. You can obtain on the one end, you can obtain value iteration, and on the other end, you can obtain policy iteration. And in fact, something that Bertsekis has also found in the 90s. So yeah, perhaps it would be more relevant to look at the control rather than policy evaluation, but I'm not sure at this point. But definitely, we need to look at that learning, and that's we need to take into account the fact that we're learning from samples.
Okay.
Question at all?
So it's really nice that you as well. I guess the place where you expect to see a benefit from hierarchy or correct time scale is when the state space actually factorizes that way, right? And so I guess you might imagine seeing that in the transition matrices as well. So I guess, I'm not sure if this is a question, but it seems the natural way to look at this is you look at the structure of the various matrices and they should match, right?
Yeah. I think. So you mentioned factorization or decomposition. I think there's definitely an interplay between first the dynamics of your environment, but also the features. And it would be interesting to look at how that time scale interacts with your choice of feature. Say you have a bad choice of feature that introduces partial observability, then perhaps there's a better time scale to match your choice of features.
Okay. Thank you very much again.